They just make this here.
Yep.
And you are free to make use of these.
Okay, so hello everyone. Thank you so much for coming. We really appreciate you being here this sunny day. So it is my pleasure to introduce the first of our speakers who comes from MIT. So make use of the sign up spreadsheet. So Sean Gunderson earned his PhD at the University of Iowa after his bachelor's degree from North Dakota State University. He's a postdoctoral associate at MIT's CAP Institute, working with the Chandra High Energy Transmission and Grating team. His research interest lies in high-resolution X-ray spectroscopy, such as developing new plasma diagnostics and line profile models. His primary work has been applying these methods to hot, massive stars, from solitary systems to complex accreting binaries. His most recent work has turned to the study of accreting white dwarfs and developing new methods to prove their accretion geometry. So Sean, thank you so much for coming. I know that the journey here must not have been easy with all of these snow and rain. And the floor is yours. Thank you.
All right. I am really excited to actually share some of this research because I get to show off the first observation IXPE has done on an accreting white dwarf, or really just any white dwarf at all. So to be more specific, I'm talking about accreting white dwarfs, also called cataclysmic variables, of which there are three general flavors. We have those that accrete non-magnetically, so you just get an equatorial disk that's falling inward onto the white dwarf, or a magnetic case where, depending on the synchronicity between spin and orbit period, you can have the material grab directly from the Roche lobe overflow point and fall onto the white dwarf. There's also an intermediate case, aptly named intermediate polars, where you get somewhat of a disk, but it gets truncated by the magnetic field, and you still get the accretion column that falls on. And this middle case is what I focused on for this IXPE measurement. So as a quick overview of the accretion geometry in an IP, we get the pileup of material as it's falling onto the pole eventually forms an accretion shock some height h above the surface. That height will be important later, but for now the thing to recognize or to know is that it's a strong shock. We get iron K emission because we're getting a maximum temperature of like 100 megakelvin, a little bit more. Really depends on the mass of the white dwarf, but something of order of this. We also get a lot of characteristic iron K alpha fluorescence, which is thought to be believed to be from reflection off of the white dwarf surface, or less common but also possible due to X-rays going back up the column before the shock. Can't really tell exactly where that's coming from, but those are the two main places it could be. Now, all the characteristics of the X-rays that we see in the spectra is highly dependent on the height of the shock. Because depending on how tall it is or how short, you're going to get different amounts of cooling, you're going to get different amounts of iron K alpha fluorescence, and a few other features related to things like this due to the spin period. So determining this height is really the main thing we need to understand what's going on in the system. So how can we do this? Well, there are two ways with current data you can. The first is to do it using just a simple, I say simple, but high-res spectral analysis to figure out what the shock height is. And then just by kinematics, you can determine what the height is based on comparing the shock height to how much energy is within the escape velocity. The other method is to look at the Compton reflection that's going to be occurring in the system, because we do have very high energy photons. And based on how many there are out to like 20 keV in energy, we should expect some amount of Compton reflection. And both of those methods get you something on the order of at most a white dwarf radius above the surface. But depending on the method you use, you can get very different numbers. So in Luna et al. 2018, they used both methods. And from the Compton reflection, they got something like 0.9 white dwarf radii. But from the shock temperature measurement, they got anything from 0.3 to 0.75. And that large range is due to an assumption you have to make about the truncation radius of the disk. Because depending on how far out it goes, you're getting closer and closer to reaching pure free fall velocity versus some fraction of that. And so that's where they had to more or less stop their analysis because they didn't have enough information to tell them what that truncation radius is or to narrow down the range between these curves. But the key thing here is that with the reflection method is that they only accounted for Compton. There should be Thomson scattering in the system. So the Compton we know is going to be over in this area. And that has a unique spectral signature due to the nature of Compton reflection. But the Thomson scattered photons, we're not going to be able to tell in an X-ray spectra, no matter how high resolution, which photons are which, because they're photometrically the same. They don't cause any energy shift. It's just an added component that may increase the flux by like 10%. So really that could be within error in the different bins. So how can we really tell the difference between a Thomson scattered photon and a regular photon? The key there is going to be in its polarization, because Thomson scattering, if it's off of a coherent surface and there's symmetry being broken, will have a polarization measurement that we should be able to measure. And thankfully, recently, the IXPE mission had been launched, which allows us to finally access polarization measurements in the X-ray band. Now, it is limited to the 2 to 8 keV region, which is why something like an intermediate polar can be a good test case of this because of having a reasonable amount of emission in 2 to 8 keV. But we also had to choose our target carefully because we need to maximize the polarization signal that we can measure in a short amount of time. Because the key factor that determines whether you can measure the polarization is your MDP 99, or minimum detectable polarization at 99%. And that is highly dependent on the exposure time. We'll get to that in a second. But the main thing is that the target of this study, EX Hydrae, was the best case to start with. Now, I list a ton of its properties here, but the two that are the most important are that its inclination angle was almost 90 degrees. It's highly inclined, and it's very close. So that means that we won't need as much time as, say, something like DQ Her that's slightly farther away. And because it's nearly edge on, any reflections that occur, we can attribute more easily to being scattering into our line of sight through forward scattering, which should maximize the polarization signal. I will also note that in this assumption here, I have not made any case of why or how there should be polarization, other than an assumption that there is scattering. In fact, there was one paper in 2004 that kind of predicted what you should see in the polarization from a white dwarf, but not from an intermediate polar, from a polar. So I admit I was kind of shooting in the dark using basic physics to say there's scattering, there should be polarization. But I also had no idea what I was going to find. So this was also kind of fun shot in the dark. But assuming an intermediate polar's physics are going to be similar than a polar's when you're close to the surface, there are two sources of polarization we can expect. The first is the source emission itself. If you have a strong enough magnetic field or enough density in a non-symmetric medium, you should expect to get some amount of source polarization. Now, for magnetic CVs, this requires a strong B field because you need to have a lot of material in the column to do that. This, like I said, that high B field can cause high density, which causes an increase in scattering that occurs here. But this will also be energy dependent because we know the emission from the column has an energy dependence as it cools from the top of the column to the base. The other location is a lot easier. That's just going to be the reflection off the surface. And by assuming that this is Thomson scattering, it should be energy independent, but it's going to be very dependent on our line of sight. So depending on how inclined not only the system is, but this accretion column to our line of sight and where the scattering happens could completely wipe out our ability to measure the polarization. So while this should be easier to understand, you can be unlucky if you choose a wrong source or the source just happens to not line up correctly. So let's say the data is taken. How do we get the measurement? Well, there are two methods you can get to measure polarization that are important for the study. The first is the usual method of using a polarization cube. This is provided in the IXPE OpSim package, which is more or less the standard way of doing things with IXPE. And it uses a frequentist approach where you're just going to statistically measure your probability of having measured polarization at each time bin and in each energy bin, and however you want to make the cube. This is the community standard, and thus it's always good to use it so you can make sure that you're getting the right results. The other method, thanks to Herman Marshall at MIT, through 3 papers, figured out a way to do this in an event-based method where you're going to track every single photon independently as it's coming in, and you can thus make this into a Bayesian approach. So you can get a slightly better measurement, either because it's a higher polarization or a slightly tighter constraint on the error bars, but they should agree. If they don't, that's something interesting. That's a talk for another day. If you want to know more about this method, I do include a QR code to the source code, or at least the paper on it, by Swati Ravi, one of Herman's grad students. But no matter the method, the standard that the IXPE team has set, and you can and they will argue against it if you don't use it, is that your polarization has to be above MDP 99. This is straight from the Phil Carrot, the PI of the instrument right now, or the head of the instrument. If you do not have a 3 sigma detection, you do not have any polarization measurement. So that is our target here, is that we need to have polarization above this number. So what does the data look like? Well, because we have a low resolution in energy space, we have to bin it up into pretty coarse bins. So that way we have enough flux and enough exposure to get out our polarization. So splitting that up in either the full band or within 2 to 3, 3 to 4, 4 to 6, or 6 to 8, we can see that the effect of going to of a spectrum where at 6 to 8, we have to get 20% polarization really to see anything. So that's unfortunately an effect of the distribution of photons. But when we look at the full 2 to 8 band, we don't see any polarization. We're below our MDP 99. Same thing for all bands above 3 keV. We don't see any polarization. But in the 2 to 3 keV band, we actually see significant polarization, up to 8% if you use the p-cube method, the polarization cube. Or if you use the queen bee algorithm, we get 7% plus or minus 2. Differences, like I said, can occur in the exact number they get, but they should be similar. But this has a very strong case of having actually been measured, because we are above 3 sigma in detection, but the Bayesian factor for the queen bee algorithm is 12.8. And if you use Jeffrey's scale, when you're above 10, you have a solid detection. So we know for a fact we have measured it in that region. But this is actually kind of a problem in a way, because we assumed we'd have Thomson scattering. So why is there an energy dependence when there shouldn't be any? Well, I kind of alluded to it already, but let's take a step back and now look at our polarization angle. So we don't really know where the scattering surface is. We expect it to be the surface, but the polarization angle can kind of give us a sense of where it is if we compare it to other known quantities. So if we compare it to the optical polarization, which is this grayish area, that is going to be orthogonal to the spin axis, assuming that the B field and the spin axis are parallel. So you're right on top, they're right on top of each other. They might be a little bit offset, but good first order assumption is that they're on top. We find, though, that our polarization in X-ray is perpendicular to the B field. Which means, ironically, that we know that we're reflecting off the surface and that they're very close to each other, the scattering surface and the B field, and thus the accretion column. So I realize now I have the wrong symbol there. I think I was copying things incorrectly. I meant to say that the polarization angle is parallel to the magnetic field, but it's perpendicular to the scattering surface, i.e., our scattering surface is the surface of the white dwarf, and it's very close to the accretion column. So we have a strong case now to say not only is the surface illuminated, but it's illuminated with enough photons to give us scattering and a couple other things that that may be important in future studies. Get to that in a second. Now, the final thing before we kind of build our diagram of what we're seeing with the polarization is whether or not it's variable. EX Hydrae has a spin period of like 4,000 seconds. So in the like 1 week's worth of observation with IXPE, hopefully we should have collected enough photons to actually see that spin period. Unfortunately, we don't see anything. So the black line is from P cube, what the polarization is in quarter phase bins. And the red line is the MDP 99 for those phase bins. So the short answer is no, we didn't see any. The long answer is maybe we did, but we just need more exposure to actually see it go above MDP 99. Because it's possible that there is, say, 10% or 11% polarization in this bin. We just statistically can't say that that's a real detection. So we know that we have 2 to 3 keV polarization. That polarization is going to be off the surface near the column, and that we see no spin modulation. So what's the picture that we can make? Well, for one, it will be spin averaged, but this is the general picture we can make, that we have an accretion column falling onto the white dwarf's polar cap, and we have like high energy 10 keV photons, hypothetically, that are, a few of them are coming out of the column, but not a lot. But we have a lot of 2 keV photons that can come from the entire column. Because it doesn't matter how hot you are, the whole column can emit softer photons much more easily and more numerous than the high energy photons. So the energy dependence that we saw isn't real in the sense that the reflection is energy dependent. We're seeing the effect of the spectrum having more flux at 2 keV than we do at, say, 6 keV. And this is important because presumably if you didn't look at that energy dependence, you would assume that there's no reflection, or at least polarization occurring. But in reality, we just have enough 2 keV photons that as the gas cools falling down, we get reflection off the surface at the polar cap into our line of sight. So this is really cool to actually say with confidence that this is the geometry of an accreting intermediate polar. When in reality, for the longest time, we just kind of assumed, and the assumption worked really well. So now that we have this picture, how do we get out H naught? Because that's what I said at the beginning was the important quantity that matters. Well, really, if I look at this diagram of an intermediate polar's accretion column, to me it looks like a lamppost for a black hole. So what if we modify a black hole's model to be used on a white dwarf? Because the geometry is effectively the same. So this is going to be adapted from Dovchek's paper in 2004, where I'm just going to assume we have a nice 2D geometry. We're going to ignore curvature. We're going to ignore some of the other effects, but just this simple picture. Well, the ratio of the incident light to the source, incident at this radius r, is just a geometric factor. And the amount of light reflected into our line of sight will be some constant fraction of that incident light. So our polarization fraction is just going to be this simple ratio, in i.e. just this component. But we don't have one source. This gets more complicated because we actually have a continuous column where the height is going to have or the polarization will have a dependence on the height. So we have to integrate. We have to imagine all of those infinitesimal slices, but we have to weight them by the amount of emission that's at each height, because we know that the column is going to emit different proportions in the delta E bin, depending on what height you're at. But we only know how to do this in temperature initially. So we have to do a little bit more modeling, and thankfully Luna et al. 2015 did this, where if you assume an isobaric cooling flow, you can connect the height in the column to the temperature just by assuming the differential emission measure is a cooling flow. And that's all that's needed here. All we need is the shock temperature and a polarization measurement and a differential emission measure. That's it. Now, as long as you have access to a plasma database, you can get out emissivities, you can model your differential emission measure, and if you do that, you can come out that the shock height in EX Hydrae is 0.53 white dwarf radii, plus or minus 0.1 due to errors and assumptions. So that was a lot of integrals to get out a simple number. What does it look like? Well, if we compare to Luna's, we're right about here, which is a perfect match to what they found from their shock temperature measurements. But a key thing here is that I had to make no assumption of the truncation radius of the accretion disk. In fact, from this, I can say what that truncation radius should be. It should be something like 10 white dwarf radii. They could probably do a better job estimating what it is, but it's closest to the blue line here. So this was computed with minimal assumptions, ignoring my simplified 2D geometry, but that's something that can be fixed. So this is really the power of using polarimetry, that you can get out the geometry directly from the measurement without having to make very many assumptions. So I can conclude from doing this observation that there is strong polarization detected from an accreting white dwarf. This was not expected, and from talking with Herman Marshall at with some of his colleagues at IXPE meetings, they were surprised that we even did this in the first place. So this is a brand new territory for X-ray polarization measurements. I determined that the scattering surface, well, I didn't give the number before, is within 15 latitudinal degrees of the spin axis. It's relatively close to the white dwarf. And the white dwarf surface is illuminated by X-rays. This is actually further evidence potentially that iron K alpha does come from the surface, because now we know the surface is illuminated by the column. I didn't detect any periodicity due to the MTP99 being so high, but that just takes more data. And that the X-ray polarization can be used to determine shock heights in eyepiece. But where do we go from here? This was the first time this was done. Well, we just need more measurements. We can do a polar now, such as VV-PUP, or a non-magnetic CV like SS Cygni, or maybe a symbiotic star, which is a completely different class of accreting white dwarf. So there's a lot of new windows that this opens up for us to understand the accretion geometry in these systems. But at the same time, I need to do better about the 3D modeling for this system, because maybe that can refine that shock height estimate and bring the error bars a bit downward so it's not 10% error. So thank you all for listening, and happy to take any questions.
Questions first from the room and then from Zoom.
That was really interesting. I had a couple questions. One was the assumption that you could model the shock just using the radiative cooling. Because as the gas goes down, there's a change in the potential energy from, 1.5 to 1.4 radius. So that's a fairly substantial amount of energy that has to be released.
Yes. So the main assumption here is for one that we are, it's an isobaric cooling flow or nearly isobaric. So the pressure is going to stay the same. And that where the energy is concentrated is going from, say, that 10 white dwarf radii all the way to half a white dwarf radii. The other half white dwarf radii as it falls down is not going to be as consequential, especially because most of that potential energy has already been converted to thermal energy in the shock.
Right. I think for half a solar radius, you can get away with that. For one white dwarf radius, it would be getting to be problematic.
I don't think that's been considered for the modeling of the X-ray spectra and like getting out the differential emission measure. This paper by Luna goes into great detail as to what the differential emission measure should be. It technically should be a slight deviation from a cooling flow. The best way to model that would be adding an extra power law, but then you lose your ability to do this step. So it's give or take.
It's not too hard in numerical integration.
Yeah, yeah.
And then the second question is the assumption that the white dwarf surface is flat, because again, half
Yep.
solar radius is significant when you're looking for 1.5.
Yes, so that was a simplification that I admit I had to do because IXPE does not have any proprietary time, and they have had a problem of data being scooped from the proposer. So this was I needed to get it published and then was going to do the more detailed modeling later. But for a first pass, it seems to work really well to assume that the scattering surface is better said to be close enough to the accretion column that you can ignore the curvature, even though it might not be. Again, that's a thing later to do with the 3D modeling.
Any other questions for Sean in the room? Or on Zoom? Okay. Yeah, I have a question. So the rotation period, can you just go into more details about what you would expect and how, if this were to show up in your analysis with further data, like how would you go about assessing these and what steps?
So I would naively expect that maybe there is one spin period that might be where we're getting a maximum amount of polarization. Like hypothetically, maybe we would see bins 0 to 0.25 and 0.75 to 1 are always below MDP 99. But maybe these two bins from 0.25 to 0.75 rise above. Excuse me. What that would tell us is that there's a asymmetry in the system given by our line of sight and the actual geometry of the accretion. So this is why I called this a spin averaged accretion column, because when you go through the detailed simulations that have been done on EX Hydrae, it actually turns out you get like a horseshoe shaped curtain around the pole, but I can't say that that is what I see because I don't know exactly what the time dependent data would say. So I have to just do the spin average, in which case you get a column because it'll smear itself as it spins in a circle. There is another period as well for the orbit of EX Hydrae, which is like 6,000, 6,500 seconds, something of that order. And there could be an extra layer on there where maybe there's a specific orbit where orbital phase that we see the polarization at is just there's a beat period along with it that kind of makes it hard to model both simultaneously.
Thank you. Okay, any final questions? So with that, let's thank Sean again. Yeah.
Really like that.
There's a central there.
So it's up.
Yes.
So we can switch to mine.
Yes, sorry.
Okay.
That. See. Yeah, where is, there it is.
Great.
And then I think I need to move the screen share over.
Yeah, so while we are setting up, I'm happy to introduce our second speaker, who accepted being invited for this talk in very short notice. You may remember Sasha's talk from last year, where you talked about the KM3 net results and that detection of these very high energy neutrino and its possible astrophysical origin. So it is my pleasure to introduce our second speaker, Sasha Plavin. Sasha is currently a BHI fellow over at the BHI, and he studies central regions of jets in active galaxies, trying to understand what they consist of and how they become highly relativistic. He focuses on the highest resolution radio interferometric observations, supplementing them with optical, X-ray, and neutrino detections. And as far as I know, you're the only KM3 net member at CfA. So thank you so much for accepting our invitation, and take it away.
Yeah, thanks a lot. Today it will be nothing about KM3net, nothing about neutrinos whatsoever, but definitely about Blazars and their jets and what is interesting about them. So I will tell about how we can use Gaia already and even more so in the future to directly localize where Blazar flares are happening. And I hope that this talk will be useful not I mean, of course, to those who are interested in Blazars and their variability, but also to those of you who are using Gaia data or looking forward to using Gaia data, especially for variability purposes. Like I'm drawing something, right?
If we.
Yeah, I guess like I click here. Oh yeah, it seems to work. Okay, indeed. So optical flares and Blazars. Blazars are known to be super variable. They change their brightness in different wavelengths, especially in optical, specifically in optical by factors of several on scales of hours, weeks, months, and all the way to years. Today, we'll focus on these scales of months and years, something that's comparable to how often Gaia observes each source. And a big question that always arises is where these flares happen. And there are generally three regions where it's feasible. Either it's somewhere in the accretion area, even for Blazars, we can see emission from there. Then it may be some regions very close to the jet base in the acceleration region, or somewhere much further away. So here I'm showing the most well-studied jet of M87. This is one of the few jets that you can directly resolve with optical, and you can get all this structure inside of it. But it's very rare. Typically, we don't see these images because optical telescopes just don't typically have this kind of resolutions that we need, aside from probably optical interferometers. And how the localization is done typically, actually, both for optical flares, for gamma ray flares and Blazars as well, is through time lags. So there is one band where we can directly see the emission and directly see the changes and the internal structure. It is radio because of radio interferometry, and there we can directly see where flares are happening in radio. Then if you have a flare that is both in radio and in optical, or like radio and gamma rays, you can look at the time lags, assume some velocity calculated from some other properties of the source, and then from the time lag and velocity, understand where the higher energy, like optical or gamma ray flares happening. This doesn't always work, of course. For one, it doesn't work with so-called orphan flares. If a flare only happens in optical, only in gamma rays, you cannot really localize it this way. Also, if you're thinking about precise localization, you need to know the velocity pretty well. And of course, this method has quite some success. This is the main method currently used to localize higher energy flares in blazars in distant agents, but it definitely has its downsides. So for now, for later, just this one. Yeah. So ideally, of course, we want to localize these flares spatially directly in the sky plane, not through time lags. And the thing we have in optical is we don't have like routine resolution at the millisecond and sub-millisecond scales. We don't have images at these scales, but we do have some measurements. And these measurements are astrometry, and using Gaia and VLBI astrometry has been shown to be quite fruitful to probe optical emission of Blazar jets. There are I saw some references here in, I would say about half of them. I'm also an author or co-author. So this most of these papers, at least those that I was heavily involved in, so we last did that for when the previous Gaia data release was released, the Gaia DR3, quite some years ago. And the thing is that the offset, basically you're looking at the offsets between VLBI and Gaia positions. Here I show just some example. In the background, there is the VLBI image. Basically, we get the images at sub-millisecond scales of Chilean radio. And the vector here shows the offset from VLBI position to Gaia position. They generally, most of these systematic offsets, they are jet aligned, so they are definitely astrophysical, and they've been already a pretty useful way to probe optical jet emission indirectly, because we cannot do it directly yet. But we also want to go to variability, and basically the overall setup that is feasible to constrain scenarios that are feasible to distinguish with astrometry data is basically like to take this simplifying assumption. Maybe like you have in optical wavelengths, you have emission consisting of two components. One is this arbitrary constant emission that is your overall jet that is several kiloparsecs long at least, or maybe even longer. It barely changes on this time scales of observation, so it can be assumed to be constant. And then there is some small point-like feature located somewhere in the jet, just always at the same position. There is something flaring somewhere along the jet. And here, the question becomes where these flares happen. And I would say that this is both a realistic set of assumptions and something that is feasible to constrain with existing and even better future observations. In this setup, it's actually quite easy to understand where the optical, the centroid of the emission lies. Basically, what Gaia can measure directly. This is the centroid of all the optical emission averaged over the PSF, and it just happens to be just a linear function of another observable quantity that is basically inverse flux. And the coefficients in this linear equation, so especially the first coefficient, is directly interpretable. It is directly the position of the variable component. So sounds simple, right? So we have Gaia observes each source several times a year typically. And we can get both the flux and the position. Look at this equation and see like both first qualitatively which way the centroid moves during flare. So either it moves close to the jet origin, further away from the jet origin, towards some specific location in the jet, and then quantified by finding the position of the flare. And this has often been the plan. There are several. I know that there are several groups who are like waiting for Gaia DR4 that is soon to be released later this year. I guess they promised December 2026. However, there is something you can already do, and the results of what you can already do with existing data is turned out to be better than I expected when I started it. So really, the issue now is that we don't have per-epoch positions in the current Gaia data release. They will only be released in about a year. So what we have now, we have light curves. So these black data points shown in the top, they are directly available. In every transit, Gaia absorbs some source, it measures its flux. This is directly available. And what we also have is not so we don't have these kind of per-epoch positions, but we have the overall linear trend, what they call proper motion. Of course, for these sources at cosmological distances, this is not a real proper motion. It's just the linear feed to the centroid motion over the observation time. But really, again, for sources, like if you look at these at the top, right? So you have the bright flare at the beginning, then the flux kind of subsides and it becomes fainter and fainter on average. And you can intuitively understand that we can at some population level try to find this effect where you see this correlation maybe like in the directions of this and compare with expectations on where flares happen. So basically, like look at these kind of plots for all sources and see like how these directions coincide. First, of course, I looked at several cases manually, and I will show just the two that representative. The first scenario is when you have a flux that is rising on average. You have some flare closer to the end of the Gaia observing period, and with these arrows, I show the Gaia proper motion. So you see that the Gaia positions are here. They are offset from the jet origin, but they are moving towards the jet origin. And this is kind of okay. You have rising flux and the Gaia centroid moving closer to the origin. And we have the opposite scenario where the Gaia flux is fading. So you have a flare closer to the beginning of the time span, and the proper motion points away from, so basically away from the jet origin. And now you can say again, like there are these scenarios that kind of suggest that in these cases, if all the interpretation is right, maybe in these cases you have that flares are happening somewhere close to the jet origin because when the flux increases, you have motion towards here. And the same scenario happens in this case, right? So when the flare subsides, you have, so if the flare is here, its flux decreases, so the centroid is moving away. But these are just two examples, and that's what I also thought at first. But now let's see the whole set. So here so on the horizontal axis is just the angle of the proper motion versus the jet direction. So 0 means the Gaia centroid moves along the jet direction, so away from its origin. And once 180, it means the centroid moves closer to the origin over time. And the color is the same color as I used in the previous slides. This is a flux trend, basically. Is the flux rising on average? Is the flux fading on average? And of course, in terms of measurements, these are completely independent, unrelated measurements instrumentally. It's so proper motion is derived from position information, flux is derived from just the brightness of the CCD. And still we see basic, so I would say like almost perfect correlation, right? So of course you can compute the significance, but it's kind of clear that among these 65 sources that have both significant proper motion and light curves available, there is almost perfect correlation. So jets where the optical centroid moves closer to the jet origin, they show like rising flares and the other way around. So this is basically a perfect correlation, and it indicates that so first of all, it indicates that our simplifying assumption seems to work out, because otherwise you would see much more of a messy picture. And also the flaring region, at least qualitatively for now, it lies much closer to the jet base than the overall centroid of the jet emission. So flares are happening very close to the jet base. How close is something I would say a few words later. So basically, this is a picture, right? So flares are happening. I just saw the flares as growing and shrinking circle here. So they are happening somewhere close to the jet origin. And what we see is the motion of this optical centroid, because this is a directly measurable, directly observable quantity. It moves back and forth. Specifically, it moves closer when the flare is brighter, and it moves away when the flare is fainter. And this is basically ubiquitous effect. Again, of course, among sources where that Gaia detects, that VLBI detects, among the sources in the sample. So yeah, the qualitative outcome is that flares close to the jet origin, they basically universally drive back proper motion. This is where flares happen for sources in the sample. Yeah, and of course the caveat is what is the sample. For now, the accuracy of how well we can localize it, I would say it's a fraction of a millisecond or a few parsecs at these typical distances. We are heavily limited not just by the intrinsic measurement accuracy, but really by this by the fact that we only have these linear proper motions. Linear proper motion fits because if you have a flare in the middle, it basically completely washes up the overall trend. If you have a flare at the end, it doesn't wash up completely, but it's still there is some cancellation going on. So it's already interesting. It's already useful. As a direct demo with real data that we can and we do localize where optical flares are happening. But of course, per-epoch Gaia astrometry that will be available, I hope within less than a year, they will release it. It will fundamentally remove these this limitation of something averaging out and washing away. And I expect the accuracy to improve by a factor of a few, actually. And then it will become even more useful because now it's just roughly somewhere around the jet origin. And everything here is we fundamentally need some anchor along the jet, and this anchor is VLBI position. VLBI positions are known to be not exactly at the jet origin. So if we with the new Gaia data release, if you improve this localization by a factor of a few, it will already be better in the sense that the accuracy will be even smaller than our understanding of where VLBI position is. So for now, we can just say, okay, it's either innermost jet or the accretion flow, not the extended jet, but this innermost jet part, it hides quite a lot because in the first millisecond or half millisecond of the jet, the first several parsecs, a lot of interesting things are happening. And the next step would be to resolve where exactly it happens. So as a summary, really the observational results we already have without even per-epoch Gaia astrometry is that so we see that optical flares, they basically universally drive Gaia proper motion for Blazars. And the flares, they occur near the jet base, within a few parsecs of what we met of so-called VLBI core, the radio jet origin. As a bigger picture, I see it not just a way to localize the optical flares, although that's very useful, and I'm too much interested in that. But also, I would say this can become the way to hunt for even higher energy synchrotron, where exactly these higher energy flares happen. Because, as I said, now you localize gamma ray flares by time correlating with radio. If you have, and there are a lot, like not a half, but a significant fraction of gamma ray flares that are orphans that are not in radio. But some of them, many of them, are also in optical, so they can be like. We can localize optical flares directly in this way, like directly in a spatial way here without relying on time correlation, and then use them as an anchor for higher energy. So I would say finishing the paper, it should be submitted soon, and of course waiting eagerly for the next Gaia data release with per-epoch astrometry. And if you have like a science case where you are waiting for per-epoch astrometry as well, maybe try proper motions already. Maybe they will be useful for your science case as well. With that, thank you, and looking forward for questions and.
Okay, I'm gonna take chair's privilege. So, can you run us through how you selected the sample? Are all of these like well-known Blazars? How far in redshift you can get? And the second question is, so in the very nice diagram that you showed, your VLBI is slightly far away from the flare. So can you, for the non-VLBI experts, can you sort of summarize why that is? And great talk. Thank you.
Yeah, thank you. So in terms of sample, for now, we can't even do like we cannot be picky with source selection because there are so these 65 HMs. These are just a sample of you have they are bright in VLBI, so they have bright radio jet emission. They are bright in Gaia, and they have non-zero kind of significant proper motion in Gaia, and basically, so yeah, they are not a kind of like large redshift, but on the order of 0.5, 0.3 to 1 is, yeah, there are a lot of this. So these are kind of pretty distant. So they are not the local universe, but they are not like the dome.
Okay. And Gaia just gives you 1 point. And then, yeah, can you explain that?
Yeah,
so VLBI, like, why do you suspect that VLBI won't fall on the flare? I mean, if the flare is bright enough, like HST1 not, which was dominating the high energy emission for like many years, why wouldn't you expect the VLBI central to be at the flare?
So first of all, what Gaia gives us? So Gaia gives us basically the coordinates, like the average coordinates over their time period with in this example, they are somewhere here. And also they give a linear proper motion. Here I show both the direction and the length corresponds to the Gaia observing period of 3 years. So this is kind of the proper motion. That's what Gaia gives. So, and for Gaia, it's pretty easy to understand what exactly it measures. It's clear that it measures to a great accuracy. It measures the centroid of all the emission that falls within its PSF. And Gaia PSF is, it's asymmetric a bit, but it's about 0.2 arcsecond. Gaussian. In terms of VLBI measures something kind of in a completely different way. VLBI doesn't measure any centroid really. It so to the first order approximation, what we measure with VLBI is the position of the kind of brightest point in radio, and it's kind of well known that this brightest point is not the centroid of anything. This brightest point is the reason why it's not directed jet origin is because here you have synchrotron opacity, you don't have synchrotron self-absorption. So you just don't see any radio or almost any radio emission upstream. And there is a big question in the astrometry, astrometry and geodesy community, how exactly this influences VLBI coordinates. But these effects are like a small fraction of a milliseconds. So it's definitely not even half. That's why I don't show here. I didn't go into detail on like what we measured with VLBI. It was used just as an anchor because we need some anchor to understand like if the shift is along the jet or opposite to the jet, and yeah, these purposes.
Great, thank you so much.
Yeah, that was a brilliant talk. Thank you. I didn't see anything that tells me how far away from the radio core the optical flare is. What I would expect to see is that on the y-axis here, the inferred distance, the centroid shift is. I would expect you to have a wide, a priori, I would have expected a wide range of displacements, but you seem to conclude that it's always like a half milliarc second,
within,
which is remarkable.
Yeah, so the way to how I localize flares now here is basically like by finding these coefficient in this linear equation, and given that we effectively have 2 points, so we have 2 coefficients and we have 2 points for them because kind of proper motion effectively gives you 2 points. That's why it's kind of pretty rough for now, so for I don't have like a final plot with properly selected sources that have reasonable uncertainty on that, but this comes from the about 25 sources that have. So for each source, I can compute X var, compute its uncertainty, and often it just ends up huge, just because there is no major flare happening, for example. And within a few tens of sources that have small uncertainties, like I think I selected uncertainties less than like a millisecond, or less than like maybe half a millisecond. I mean, it's still fast. So among those with small uncertainties, all of them fall within plus minus 0.5 milliseconds of the Gaia position. So for now, I think that's kind of the most accuracy we can give, and yeah, I agree. This is kind of quite remarkable. I didn't expect this analysis. Like I didn't even expect this plot to be so well kind of separated between different colors. I just kind of did this analysis. I started this analysis as a check. Okay, like maybe this is something in preparation for the next Gaia data release, but it ended up quite fruitful.
Hi, thank you. This is a really interesting talk, especially this plot. My question is, have you done a similar analysis of the field of the eye? Like, what kind of shifts do you get for radio flares?
Yeah. So I personally didn't do, but it's an ongoing kind of, so I know some people who do that. But it's somewhat for different purposes, right? So the reason why it's astrophysically interesting to do it with optical is that we have astrometry with accuracy much better than we have images. With radio, we have astrometry and images at about the same scales. So there is still some effects, like some smaller effects you can dig out of that. But it's less of a ubiquitous effect. It's more like for some sources with heavy kind of contribution of the jet. It's not even centroid, but there is some connection. But it's astrophysically just a bit less relevant. It's more relevant for astrometry and geodesy.
Any final questions? From Zoom or in person? Oh, so let's thank Sasha again. Both. Yeah, so we'll see you next week, and we will not be having a high energy seminar 2 weeks from now because of proximity to Chandra deadline.